Alright, ladies and gents, here is the next section we're going to be talking about, is the application of integrals and rotation. So we're going to be finding volume of solids. So the first thing I want to do is I want to make sure we understand what integration means. So for example, we have our equation here, f of x equals the square root of x plus 1. And say I wanted to find the area under the whole curve. Well, we discussed that if we split this up into many chunks of rectangles and found the summation, that will give us an approximation of the area under the curve. So the more rectangles we have, the more accurate the area becomes. So we are taking the area of each rectangle, which is length times width. The length of each rectangle is going to be the same. That's going to be our dx. And the height of each rectangle is going to change. So the distance from the x-axis to this equation, that's going to be our y value, which in this case is just f of x. So our area for under a curve is the summation of the area of each rectangle, so f of x times dx. In this instance, it's square root of x plus 1. So what we're going to talk about is what the volume would look like if we were to rotate it about an axis. Say, for example, we took this graph and we rotated it about the x-axis. Like, what would that look like? We're going to take this line and spin it around the x-axis. If we were to spin this line about the x-axis, so it just went all the way around, it would look something like this. So we took our line, our curve I should say, and we spun it around, and now we have somewhat of a cup that's not flat in the bottom, and we are asking to find the volume of the solid. So we're going to find the volume of this new shape that we just found. Yeah, the big difference between what we were doing before and now is just we're adding one more dimension. Here we're just dealing with area, but here we're adding a new dimension and we're talking about volume. So let's talk about how we found the area in the first place. We found the area by finding rectangles under the curve, but now we're spinning it. So we're going to spin these rectangles. We're going to spin this whole rectangle around 360 degrees about the x-axis. So this here is representing the the volume of this disk at this one spot. Just like this is the area of one rectangle, this is the volume of one disk. Now let's pull this little chunk out and see if we can come up with the equation to find the volume of that shape. So let's pull this little figure out. Let's read and write. I'm going to... I guess we have a round surface because we turn it around 360 degrees. We have a little bit of a height. And a new disk. Okay? Okay, I want to find the volume. Volume is area times height. Our area for this guy, area of the face, is what's the area of this shape? That's going to be area of a circle. So this is going to be pi r squared times our height, which is this distance right here. So if we look back at the original equation, this distance was our length of the rectangle, which was our dx. Our change in the x. Now how are we going to find our radius? How are we going to find our radius? So our radius was from, there's our center, it goes all the way up. So it looks like our radius is the y value. So in this case it's going to be f of x squared. Alright, so far so good. So this will give you the volume of one disk cut out of this whole shape, out of this whole figure. So this equation gives you the volume of one disk out of the whole figure. But what I'm interested in is the volume of the whole figure, not just one disk. I want the volume of the whole figure. So we're going to take the summation of infinitely small disks cut out of this figure. So basically, when we talk about the summation of area or volume, we're going to be using the integral. The integral of our equation is going to be pi times f of x squared, which is going to be our radius squared, times our dx. Now, since pi is a constant, we learned that during pi day. Pi is a constant, it's 3.14 approximately. We can bring that outside the integral. So, basically when you're trying to find the volume of a solid using the disk method, you're going to use this equation. You're going to do pi times the integral of whatever your radius squared is times your change in the variable. It's not always going to be dx, it might be dy. This is not going to always be f of x, it might be a function of y or a function of z. Those will change. Also, they will get more complicated because we'll have more than one curve at one time. But this will give you a good idea of what we're going to be dealing with in class. Alright, ladies and gents, for your homework, I want you to practice sketching these shapes, because most of the time that's the most difficult part. It's not the integration, it's the actual visualizing what's going on. So I want you to sketch f of x equals x squared, rotate about the y-axis. So that's going to look something like we just saw, maybe like a cup. I want you to see f of x equals 2x, rotate about the x-axis. So 2x, that's a line. Rotate about the x-axis, going to look kind of like an hourglass. And f of x equals x cubed, rotate about the y-axis. Okay, try those out. Make them nice and pretty. I know you're not artists, but do the best you can.